Okay, so the atmosphere. Many of the things that the atmosphere does, properties that it has, is very similar to water. It is a fluid, and therefore it does move through convection. It goes from a hotter area to a colder area, and it does so actually faster than water, but it cannot absorb as much heat as water, nowhere near to it, but it still does have the effect of distributing energy. And I got a little ahead of myself. Actually, what I want to talk about first is the fact that it shields us. Probably the most important thing is it shields the Earth from high energy radiation. And as we'll see in a minute, that particular property of the atmosphere was not always there, and it was acquired from living organisms, which is kind of a unique part of the whole story of the history of Earth's atmosphere and its importance to life. So, but that's probably, like I said, probably one of the main functions is the fact that it does reflect much of the harmful radiation from the sun. It also distributes energy, like I just said. It heats up, expands, moves through convection, displaces that energy, and then loops around in currents very similar to ocean currents, but with some differences, which we'll see. And then another thing that also is similar to the heat disbursement is the fact that it also delivers nutrients. So if you recall, one of the things biologically, one of the functions that is served by ocean currents was the fact that the deep ocean currents will flow along the ocean floor and scoop up a lot of organic waste that's on the bottom and bring it up to the surface and acts as fertilizer and nutrients for those food chains there in the ocean. Similar things done both on land and in the ocean, starting on land, of course, with dust and dust storms. And this is a way that this is one of the ways in which the dust is actually mineral nutrients. It's bits and pieces of the rock. That's where plants primarily get their mineral nutrients from. Is the rock, is the crust of the earth. And so this serves the atmosphere. The gases that are in there serve to distribute those around the world. So that's nutrient distribution. Another property of the atmosphere that comes from one of those much smaller components of the atmosphere, but one that still serves a very vital function, is the fact that we have certain greenhouse gases like CO2 that are in the atmosphere, and these gases basically trap the sun's energy. In other words, the sunlight hits the earth and reflects back off. Some of it is absorbed, of course, and without these gases, then that energy would just be reflected back out into space. But greenhouse gases do capture part of that, some of that, and keep it trapped here on Earth. It's a very similar mechanism to what happens in your car when the sun goes through the windows of the car and reflects off the interior, but then it doesn't have enough energy to get back out through the glass. That's why your car gets so hot on the inside. It is also the way a greenhouse itself, plant house, is designed to keep it warm. And so these gases serve the same function like the glass in your car in a greenhouse of trapping those reflected radiation back here at Earth's level, and therefore bringing it up by 33 degrees Celsius. Now, that's a lot for global temperature average. When you consider that the average is about 16 degrees Celsius. So that would put you below 0 Celsius, which means most of the water would be what? It'd be frozen. Now you would have, theoretically, ice or water underneath with a very thick ice layer on top. But a lot of it would be, if not all, certainly the whole Earth would be covered in ice. And we would have maybe some oceans below it, but that would be the effect of having that high of a temperature. So fortunately we have these greenhouse gases in the atmosphere, and that brings our temperature up to one where there's enough liquid water to go around. Okay. So those are some of the primary functions that your atmosphere's particular properties have. We're going to go into a little bit of detail about each one here in a minute, and how they are important for life. So first we'll look at the composition. So this is one of your basic, over here, one of your basic properties of the atmosphere, what it's made out of. 78% nitrogen. And nitrogen gas, N2, is an inert gas. So that's a good thing in a way, that it just kind of like balances everything out. But much of that is not available for living organisms, even though we need nitrogen. There are bacteria that can convert this, and we'll go into more details later about how that whole process works. But for the most part, that nitrogen just kind of hangs out in the atmosphere. And then we have 21% oxygen. So this is the interesting part of the story right here, I think, is that this level of oxygen is a reactive element. Okay, it's what allows things to burn, for example. As a matter of fact, the combustion process is very similar chemically to what happens when you digest food in your through respiration in your cells. So that therefore it would tend to react with things, and without the ongoing production of it through photosynthesis, we know that plants, of course, take in carbon dioxide and water and make oxygen and glucose out of it. Without that ongoing production of oxygen, you would not have, where'd it go? The ozone layer. So good job, Group 2, you got that right, which is the part that blocks the high energy radiation. Okay, because ozone, oxygen is O2. Does anybody know what the formula for ozone is? O3. O3, right. So it's actually, this is where the ozone layer comes from. Now the ozone layer is not a static layer that's just kind of hanging out there and there's a certain amount of it. It's constantly generated by ultraviolet radiation, kind of ironically so, in the atmosphere, hitting oxygen gas, and then forming ozone, and ozone is very effective at blocking more UV radiation from getting there. So theoretically, without this happening, there would be pretty much life on land would not be possible, at least with the organisms the way we know they are, and perhaps not even in the first couple hundred feet of the ocean. So there was life before photosynthesis, and there was a long period of time where photosynthesis existed, but the oxygen did not build up to the point where it can make this ozone layer. But a lot of scientists believe that prior to that, like I said, nothing lived on land, and most of the bacteria that lived had to live a certain depth underwater with the water protecting them from the UV radiation, because bacteria are actually very, very sensitive to UV radiation. So that's why I said it's kind of a unique part of the story, kind of an interesting thing, that life begat life, so to speak, and that without this, these photosynthetic organisms, starting with your cyanobacteria, doing photosynthesis and eventually producing enough oxygen that we get that ozone layer up in the upper atmosphere, things would be much different. All right, so and then the rest of what you have there, argon is just kind of it's a inert gas, so it doesn't really do anything. It's mainly the product of radioactive decay over the many years. CO2 is in there. This is the one that everybody's concerned with global climate change. It is a greenhouse gas. At this point, it's about 400 parts per million, so that's 0.04. Where's that 0.4? It's less than 1%. Let's put it that way. And then, so helium, you got to mix your other ones. That's why I put the ... because there's, of course, all the other gases in the atmosphere, but they're much lower levels. Any questions about composition of the atmosphere, and in particular how the oxygen we have is there because of the plants that are on Earth, mainly the phytoplankton in the ocean, but also your forests and everything else produce that oxygen. It would not be here if it weren't for that. It's not that the oxygen would go away; it would react with other things and become a mineral. Actually, a lot of oxygen is still in the form of minerals in the crust of the Earth, but we wouldn't have that free oxygen in the atmosphere, O2, if it weren't for this process. Okay, so the atmosphere is layered, and this is just something, really, these layers that was determined just by this particular property that they observe in them. So the way they came up with these layers, they didn't like set a height or something like that. They just said, looked at the way temperature behaves in each layer. We'll get to that one. But you might see a pattern here. Okay, so the troposphere is where everything happens, so to speak. That's where we are. That's where about 98% of the gases of the atmosphere occur. That's where all weather occurs. Any kind of water vapor is going to be in the troposphere. It doesn't make it up in the stratosphere. It goes up to between 8 and 16 kilometers, so I just put a 12 in the middle there. As we go up through that, it does get colder. So hopefully you guys are aware of that. If you can remember that, then you can remember the temperature changes that occur in the other ones. because you do need to know the order, and you do need to know some of the properties of each. Really, only the first two layers are the only ones that really have properties that are particularly important to us. And then, like I said, the temperature change that occurs in each one. But it was the temperature. The temperature changes was how they came up with these layers. So, like I said, as you ascend, as you go up, it does get colder. Temperature does decrease. Then you hit a point where that temperature evens out and then starts to increase. That's what we call the stratosphere. Air is very thin up there, and probably the claim to fame and the thing that's most important to know about this particular layer of the atmosphere, this is where you find the ozone layer, which helps block out, of course, radiation. So the temperature increases during that, and then after that it switches around and starts to decrease again. Nah, I can't give that group A, it's too general. So it decreases through the mesosphere, and then you hit a point where you hit the thermosphere. Now, the thermosphere is technically hotter, but also in some cases much colder. The fact is that the changes in temperatures that occur in these things are a combination of two factors. That's why you kind of have a zigzag thing. Temperature in the troposphere gets colder as you go up because the air is getting thinner, and the air molecules are what holds the heat energy, and therefore it's less air molecules that have heat energy to hit you, means you're going to feel colder. Okay. But then when you get up to the stratosphere, the air is very thin. Like I said, about 98% of the atmosphere is in the troposphere. That particular effect is countered by simply the radiation from the sun, the heat from the sun. So that factors in there. Honestly, not being a meteorologist, I really don't know what the temperature change in the mesosphere comes from, why it starts to get colder as well. And maybe it's just because you're getting close to being in outer space. When you hit the thermosphere, you're pretty much in outer space. Okay, there's very few molecules around there. However, since the thermosphere itself is so blocked so unblocked, unguarded from any other layers, that when the sun's radiation does hit molecules there, they can get up to like 4,000 degrees. Okay, but if you don't have any molecules there, technically the temperature of empty space is going to be close to absolute zero. I mean, theoretically, it is absolute zero. You say you can't have absolute zero, but you can't have matter that has a temperature of absolute zero. But you know, it's one of those physics things that I don't completely understand. But anyway, so when you're in the shade, basically in the thermosphere, it gets super cold, like negative 272 point whatever. But the molecules that end up being in the sunlight, they're actually radiated up to temperatures of around 4,000 degrees. So it's kind of crazy in the thermosphere, but the fact is that it doesn't really have a huge impact, or maybe much impact at all on life on Earth. And just remember that particular property of it. And I've got diagrams here to help explain that a little bit better. Any questions about the layers of the atmosphere? So memorize that order, memorize the temperature changes, and memorize what particular ones in the, really it's only the troposphere and the stratosphere that are significant, what's special about them. So weather of course is really the interaction of both the atmosphere and the hydrosphere. The water cycle is a big part of it, but part of weather is winds. There's certain wind patterns that exist due to the fact that the Earth gets uneven heating, and it gets that uneven heating because it is a sphere. So I'm porky pig here. So, granted, from the sun's perspective, the poles are a little bit further away from the sun than the equator, but that's really not what it is. It's not a distance thing. It's the fact that when you have sunlight energy hit directly, it's just like if you were getting hit directly. You know, if somebody were to come up and punch you squarely in the stomach, then you're going to feel that impact a lot more than if somebody punched you like on the shoulder and it kind of glanced off. Well, the poles, when the sun hits it, that's at an angle, so a lot of it is reflected, or the temperate areas as well. And that's why, as we mentioned in the question at the beginning, the polar areas actually reflect off more heat energy then hits onto them. It's kind of a strange concept, but it works that way. So it's that angle of light that causes you to get, of course, as you might imagine, the most energy at the equator throughout the year. And then from there, that air at the equator then heats up and moves from hot to cold, which is what we call convection. So it moves, goes along and sinks down and wraps around. Now I'm not going to go into all this part here because I've got a diagram that does a much better job of that. But that particular motion, your north to south winds, is caused by that. It's the air heating up the equator, moving towards the poles. It actually drops down at 30 degrees, and then that turns another air cell. There's actually 6 convection cells that exist on the globe. So that, with that alone, you would have just north and south winds going from equator to pole and back. But of course we don't. We have easterly and westerly winds, trade winds as they call them oftentimes. These are a result of the Coriolis effect. And the Coriolis effect is just simply the property of anything that is either rising from or descending to a moving sphere like the Earth, because of course the Earth is spinning. So the best way perhaps to visualize that is if you were standing with one foot on steady ground and you put your other foot on like a conveyor belt or something that was moving, it would twist you, right? So if you're going up, you would twist upwards in a particular motion, and if you descended down there and you landed, it would twist you also in the opposite direction. So that's basically the effect that it's had because the Earth being a rotating sphere, the equator moves the fastest. It all takes the same time, one day, for it to go all the way around. But if you're at the equator, in one day you're going to be traveling 24,000 miles. So 1,000 miles an hour, you do the math. So that's the fastest point there. As you go up towards the poles, you basically get slower and slower because the whatever the geometric term is for that parallel that goes around is much shorter, or it gets shorter as you go towards the poles. Technically, if you stood at the very apex of the axis of rotation, you would just basically go around in a circle and have no linear distance covered by the end of the day. I've always wanted to do that, just stand there for one whole day, 24 hours, and just rotate. But who knows? Bucket list. So anyway, so that is the basis for your twisting and the type of motions and stuff. It is called the Coriolis effect. It is why storms will rotate in one direction in the southern hemisphere and the opposite direction in the northern hemisphere. It is not, sorry to break your, burst your bubble on this one, it is not, it has no effect on toilets. Okay, so there's a popular myth out there that toilets in the northern hemisphere go one direction, and in the southern hemisphere they go the opposite direction. That is not true. They go the direction they do based upon the design of the toilet itself. The Coriolis effect requires, I don't know, at least 50 feet or so of fluid, of air or water, to be affected by this difference. If you think about it, you're talking about stretched along the globe. To actually have that much difference of speed to make it twist, you have to have much bigger volume. Unless you have a 50-foot toilet, then if you got that, then go ahead, go home and flush away and watch what happens, and then move down to Australia and try the same thing. But anyway, that's not. That is a popular science myth. And of course, then so that sets up your basic major wind patterns, and then you have localized ones that are going to occur because of mountains, valleys, and the difference in land and water. The fact that land will heat up faster and cool down faster than water because water has such a high specific heat. So you see when one area is hard. This is what we do. This is what we get here in Florida in the afternoons, because the peninsula, being land, heats up faster than the water on each side, and that rising air creates like a chimney effect, and that pulls in the water, the humid water from the Gulf Stream around us, and that gives us our afternoon thunder showers and rains and stuff that we see in the summer as all that water vapor condenses out. So that is some of the things, some of the forces that drive the different wind patterns we see. So, any questions about that? Like I said, we've got a diagram that'll make that look a lot better. You'll see in the notes there. The seasons. Okay, this is a popular question on the exam, and it's certainly the seasonal change is a very important concept. Thanks to environmental science and to life and the biosphere, etc. But I think the reason why they like to ask this on the exam is that this is a very common. This is one of the things that when they ask people on the street about certain scientific concepts, you know, that people have no clue on. Okay, a lot of you did though. In your pre-test, I don't know about this class in particular, but in the pre-test overall, most people got this right. So that's good. It is a middle school science concept, but apparently a lot of people by the time they're 20, 30, or whatever forgot it. So the seasons are due to the tilt of the Earth's axis. If I could get a volunteer to be Mr. or Mrs. Sun, that would be great. I'm pretty sure this lamp is not shocking people anymore. Anybody? Oh, this makes more awesome.
You know, your hair could probably substitute for the light source there.
And that's a good thing. I mean that kindly, by the way. All right. So, what you'll notice about the globe, and you'll see this if you see most globes that are mounted on a stand, etc., is that let's get over here, camera. It is on an angle there. See the axis here when it rotates, and so that is because of the fact that the Earth's axis of rotation, which it spins around, is at about a 24 degrees angle from perpendicular to the plane of the sun. In other words, if it was perpendicular, it'd be like this. Okay, but it's not. It's like this, and that actually has a lot of good consequences. So if we go over here, if it's this time of year on this side of the sun, what season? Can you see it?
Yes.
Awesome. Thanks. What season would that be?
Summer.
Summer! Yeah, see how it's light on the northern hemisphere primarily? Then you're going to move along here. We get to here. Any ideas? If you can see from here, this angle, the globe is half light and half dark.
Fall.
This would be fall, yeah, if we're going toward forward. And then we get over here. And what do we have? Is it flat there? What do we have? Winter. Winter is coming. So there you have your seasonal changes. All in a nutshell, happens very periodically, you know, close to the same day every year, and that's just a calendar change. It's really the same. Thank you very much. Earth Day, as they say, every year, that we will have that particular change. I want you to think for a second what that does for organisms. What's that going to mean for biodiversity? Do you think that having those kind of changes every year to deal with, is that going to increase or decrease biodiversity? Increase it. Why? Because you got changing conditions, right? Environment? Is that you, Mr. Harris, said that? Yeah. Good. We looked at this a little bit, if you remember, when we talked about the wetlands out here, the fact that the wetlands are a very biodiverse environment because part of the year they're flooded, part of the year they're dry. As a matter of fact, that flooding is typically because of seasonal changes. So what you have is you have a wider variety of organisms because you have some that are adapted to one part of the year, one type of climate. And by the way, climate is the main factor that determines what kind of organisms you'll have, adaptations. And then you're going to have some that are adapted to those. You've got organisms like deciduous trees that are very highly adapted to it, so they lose their leaves and everything. That sets up a whole new type of ecosystem dynamic every year. And so consequently, that constant change back and forth, since it is regular, since it's not kind of like unexpected, it does happen on a regular basis and over thousands of years, then you have a wide variety of organisms that adapt to that. The most biodiverse place in the United States, the continental United States, is in the Appalachians. That's a temperate area. So that gives you an indicator of how much that particular changes and stuff can spawn this type of biodiversity. All right, so that, and also you think about energy distribution. Because of that, the sun's focus is not just over the equator all the time. It goes back and forth throughout the year between what two latitudes? What are the name of the latitudes that the sun travels between? Yeah.
Tropic of Capricorn and Tropic of
Right, the Tropic of Capricorn and the Tropic of Cancer. We have the Tropic of Cancer in the north, Tropic of Capricorn is in the south. On the solstice, which is the first day of summer, the first day of winter, the sun's rays are directly over that particular point. That's what they call the tropics or tropical, just means that those areas of low between those 2 points. The Tropic of Cancer, by the way, is I believe it goes right through the northern latitudes of Cuba, so it's not too far below us. We're almost tropical here. But so that's another positive property of that, just by the fact that the Earth, instead of being one way or another, it ended up being at an angle to the plane of the sun in its rotation. Just a pure chance, I would say, I guess. All right, so that is an important factor, of course, in climate and weather and all those other kind of things. And also, you should understand, as far as weather goes, it is mainly brought about by the movement of what we call air masses. And air masses are just simply sections of the atmosphere that, because of where they formed, whether they formed near the poles or the equator, or whether they formed over land, humidity, or the ocean, will have certain temperature properties and certain humidity properties. Humidity being the amount of water vapor that's in it. So if it's over a tropical ocean, hot and humid. If it's over a polar land area, polar continent, cold and dry. Polar ocean, cold and humid. Granted, a warm, humid will have more water vapor in it than a cold, humid, but they still have higher levels of water vapor in them. And so these air masses are basically pushed around by the focus of the sun. So when it does that, these air masses move along. When these air masses, different air masses, interact with each other, that's when you get your weather occurrences. That's when you get your precipitation and storms and winds and things like that. That boundary where they occur is called a front. So you hear this, a cold front means there's a cold air mass that is moving in the direction of whoever's talking about it. And so this also is why we have a hurricane season. It's why there's rainy seasons in the tropical parts of the world. You know, if you've ever lived there, if you know people that have, they don't really experience, of course, the temperature changes, but you do have a rainy season every year. That's because the sun's rays are pushing an air mass through that's going to go back and forth across the globe and come back around the same time every year. When we get our hurricane season, like we're in now, it's at the end of summer, and actually the sun's focus is getting closer to the equator. It reaches its apex at the beginning of summer in June. So by late July and August, that focus is moving down towards the equator. That means that cold air masses from the northern areas, from Canada and those areas, are actually, even though it doesn't feel like it, they're actually starting to descend down. And so when you get your warm or hot, humid air masses from Africa traveling across on the Gulf Stream, if they hit those cold air masses, that's when you get the potential for hurricanes. So, and by the way, the hurricane is just because that's where the Coriolis effect kicks in as well. It's just mainly a lot of winds moving because of the differences in temperature and the condensation and precipitation that occurs through that. But if they are big enough of all those storms together that they actually start to rotate, and that rotation actually makes the storm stronger. Any questions? Weather, composition of the atmosphere, layers, etc., etc. All right.